Welcome, everyone. Today, we are focusing on a pivotal phase in machine learning operations, orchestrating model training. We will explore how to transition from local notebook experimentation to robust, automated training scripts running at scale in Azure Machine Learning. Let us get started. To begin our journey into model orchestration, we must first discuss the transition from notebooks to training scripts. As a senior machine learning engineer, you know that while Jupyter notebooks are fantastic for early data exploration, they're inherently fragile for production workloads. What we need is a structured approach. We achieve this by extracting our core training logic into standalone Python scripts. The basics involve taking your data pre-processing and model fitting code and saving it as a clean train.py file. Why is this critical? Because scripts can be version controlled, reviewed, and automated. How do we execute this in Azure? We submit what is known as a command job using the Azure ML CLI or SDK. For a deep dive insight, understand that a command job is a paradigm shift. It completely decouples your code from the underlying infrastructure. You tell Azure what script to run and what compute to use, and Azure handles the provisioning, execution, and teardown automatically. Let us examine this architectural shift on the screen. On the far left, we start with our interactive notebook, our experimental sandbox. Following the arrow, we perform an extraction, pulling the core logic into a clean, modular Python script labeled train.py. This script is then passed into the central node, the Azure ML command job. Notice how the command job acts as the master orchestrator for this single task. It simultaneously pulls in your requested compute target and your required data assets. The compute executes the script against the data in a secure container, ultimately outputting the final trained model on the right. This visual represents the fundamental first step of MLOps, standardizing your execution. Now that our code is running as a script on a remote cluster, we face a new challenge: visibility. How do we know what the script is doing? This brings us to MLflow. What is MLflow? It is an open-source platform natively integrated into Azure Machine Learning, designed to track the entire machine learning lifecycle. The basics are simple but powerful. As your script trains the model, MLflow captures the hyperparameters, the performance metrics, and the physical model artifacts. Why do we mandate this? Because when you submit a job to a remote compute cluster, you no longer have the instant visual feedback of a local notebook. MLflow provides a centralized dashboard for this telemetry. How do you implement it? It is as easy as adding the mlflow.autolog command to your script. Our deep dive reveals that this creates an immutable, auditable record. If a production model starts degrading 6 months from now, you can look at the MLflow run and instantly see the exact data and parameters used to build it. This sequence diagram illustrates the seamless integration of MLflow during script execution. We start on the left with our train.py script. The very first action it takes is calling mlflow.autolog. As the script enters the model training phase, MLflow sits quietly in the background. As training progresses, the script naturally generates metrics like accuracy and loss, as well as the final model artifacts. MLflow intercepts these outputs and securely synchronizes them directly back to the Azure ML workspace. The workspace then locks this data in as an immutable record in your run history. By automating telemetry, your data scientists never have to manually write print statements or save local files again. To run our MLflow-enabled script in the cloud, we must tell Azure ML exactly how to handle it. We do this using a YAML configuration file. What is this? It is a declarative manifest that defines the complete execution context for your script. The basics revolve around 3 core pillars: identifying the source code directory, specifying the software environment, and providing the exact terminal command to execute. Why do we use YAML instead of UI clicks? Because this is infrastructure as code. It guarantees 100% reproducibility and permanently eliminates the dreaded "it works on my machine" syndrome. How do you build one? You simply write a YAML file that maps your local /src folder, defines the command python train.py, and links to a specific Azure compute cluster. Diving deeper, this YAML file allows you to pass dynamic inputs. You can alter the dataset or tweak hyperparameters directly in the configuration file, entirely without touching or risking your core Python logic. Let us break down the anatomy of our YAML configuration using this block diagram. Inside the top box, representing our manifest, we define 4 strict parameters. First, the code path, pointing to our script. Second, the environment, telling Azure to pull a specific container equipped with scikit-learn. Third, the compute, explicitly naming the target hardware cluster. Finally, the inputs, where we pass dynamic values like learning rates. All of these configurations flow into the Azure ML Orchestrator. The orchestrator reads this blueprint, provisions the exact Docker container on the requested hardware, and cleanly executes the training job. It is a highly controlled, standardized deployment mechanism. Once you can run a single script reliably, it is time to scale. Finding the perfect model requires testing dozens of configurations. Enter the sweep job. What is a sweep job? It is Azure ML's mechanism for automated hyperparameter tuning. The basics involve defining a search space A range of possible values for parameters like learning rate or batch size and choosing a sampling method, such as random or Bayesian. Why use a sweep job? Because manually tweaking variables and rerunning scripts is incredibly inefficient and wastes valuable engineering time. How do you implement this? You simply take the base command job YAML we just discussed and wrap it in a sweep configuration, telling it which metric from MLflow to maximize. For a deep dive into cost optimization, we apply an early termination policy. If a specific script run is clearly underperforming compared to the others, the platform automatically kills that run, saving you massive amounts of compute budget. This flowchart captures the immense power of a sweep job. On the left, our sweep job configuration feeds into the sampling method engine. This engine automatically spins up multiple, parallel executions of your exact same training script, each with a slightly different hyperparameter shown here as different learning rates. As these scripts run, they constantly report back to the Evaluate MLflow metrics node. Here is the brilliant part. Notice the dotted line to early termination. If run 3 is failing miserably, the system kills it immediately. The successful runs continue until completion, ultimately yielding the single best model output on the far right. This is automated scale at its finest. As your enterprise architecture grows, single scripts become too complex. We must modularize our code into components. What are components? They are self-contained, highly reusable blocks of code packaged with their own inputs, outputs, and runtime environments. The basics of component design involve breaking a massive, monolithic script into logical steps, a specific script for data preparation, and a separate script for model training. Why do we enforce this? Because components prevent code duplication, establish firm standards, and are the essential building blocks for creating automated pipelines. How is this done? You take your script and its YAML and register them as an official component asset in your workspace. Taking a deep dive, this creates a shared organizational library. A data engineer can build a complex, highly optimized data cleaning component, register it, and 5 different data scientists can instantly pull that exact component into their own distinct workflows. Observe the refactoring process on the screen. We begin with a massive monolithic script at the top, which is difficult to maintain and debug. We push this through a refactoring phase, breaking the logic down into distinct, single-purpose Azure ML components. We now have Component 1 strictly handling data prep, Component 2 handling model training, and Component 3 handling evaluation. Finally, all 3 arrows lead down into the workspace component registry. By storing them in this centralized database, these scripts transform from isolated files on a developer's laptop into governed, enterprise-wide assets ready for orchestration. With our scripts modularized into components, we can now achieve full orchestration using Azure ML pipelines. What is a pipeline? It is an automated, interconnected workflow that sequences your machine learning components. The basics involve stitching these components together, explicitly mapping the output data of your prep script directly into the input of your training script. Why do we build pipelines? Because they guarantee end-to-end automation. They ensure that data ingestion, processing, and model training occur in a strictly controlled, repeatable chain. How do we author them? We use the pipeline decorator in Python to define this exact data flow. For a deep dive architectural insight, pipelines allow for heterogeneous compute. You can configure your pipeline to execute the data prep script on a highly cost-effective CPU cluster, and then seamlessly pass the clean data to a high-powered GPU cluster just for the training script, optimizing both speed and cost. Let us trace the data through this pipeline orchestration diagram. We initiate the flow on the left with our raw data asset. This feeds directly into Step 1, our prep component. Notice the arrow connecting Step 1 to Step 2. The system automatically passes the clean data output directly into the train component. The train component does its heavy lifting and passes the raw model into Step 3, the evaluation component. If the model passes our quality thresholds, the pipeline concludes by registering the final model. This visual perfectly encapsulates what it means to orchestrate model training, moving from raw data to a registered asset without a single manual intervention. To reach the pinnacle of MLOps maturity, we must automate the execution of these pipelines using GitHub Actions. What does this mean? It means using external CI/CD systems to automatically trigger your Azure ML pipeline jobs whenever your source code changes. The basics are simple. When a data scientist updates a training script and merges that code, GitHub detects the change and automatically submits the pipeline job to Azure. Why is this necessary? Because manual script execution relies on human memory and is prone to errors. Automation ensures rapid, consistent delivery. How do we configure this? We store our Azure Service Principal credentials securely in GitHub Secrets and write a YAML workflow file that triggers the AZML job create command. Our deep dive reveals the ultimate security posture. By enforcing branch protection rules, we mathematically guarantee that training pipelines only ever execute on production compute when the code has been rigorously peer-reviewed and approved. This sequence diagram maps out the fully automated CI/CD workflow. It starts when the data scientist merges a pull request containing an updated training script into the main branch. This merge event instantly signals GitHub Actions to trigger the CI/CD workflow. Acting as our secure proxy, GitHub Actions authenticates with the Azure ML Workspace and programmatically submits the pipeline job. The Azure ML Workspace takes over, executing the orchestrated steps, prep, train, and evaluate. Once finished, Azure reports the success status back to GitHub Actions, which notifies the developer. This is hands-free, enterprise-grade model training. Let us tie all these concepts together with a highly impactful, real-time use case. Consider Prosware, a fast-growing healthcare startup. They have developed a critical diabetes classification model that integrates into a web app for medical practitioners. The challenge: medical data drifts over time, meaning the data science team must continuously update the training scripts and retrain the model. Because they operate in healthcare, manual execution is too risky and downtime is unacceptable. The solution is the exact architecture we just built. Prosware uses feature-based development in GitHub. When a scientist improves the training script and merges the code, GitHub Actions automatically authenticates to Azure and triggers the componentized training pipeline. The deep dive takeaway here is scalability. Because they modularized their scripts into components and automated the orchestration, when Prosware decides to build a heart disease model next month, they can reuse the exact same data prep scripts and deployment pipelines, saving months of engineering effort. Our final diagram illustrates Prosware's operationalized architecture. At the top, the updated train.py script is merged, hitting our GitHub Actions trigger. This securely submits the job to the Azure ML pipeline. The data flows first into the shared data prep component, ensuring strict data cleanliness standards. It then passes to the specific diabetes training component. Following training, it undergoes automated evaluation. Upon passing the rigorous quality thresholds, the model is seamlessly promoted, updating the live Prosware web app used by doctors. By mastering the orchestration of training scripts, you empower your organization to deliver secure, scalable, and life-changing AI solutions.